Start. So today, hopefully, I will finish this lecture. Uh, After mid, we have started with this topic, that is the control area network bus. In short, is CAN bus, or you can say CAN protocol. So this is an embedded protocol, embedded system protocol, specifically designed for automotive vehicles. And we have started talking about this CAN bus or control area network bus, giving some example of this figure, that where the functionalities or the different functional system of a automotive vehicles has been highlighted, and each of them can be treated as one device. So let's say n number of devices are there. Now, if they like to interact with each other, in that case, it will be a fully connected network. So in that case, that the connectivity complexity will be higher for this sort of environment. So to avoid this connectivity complexity, the CAN bus has proposed a solution that each of the system will be equipped with a CAN controller or CAN protocol driver, and related hardware will be implanted with the system. Then they can communicate with each other via one high speed, or you can say that in one end it is high speed bus, and in one end it is low speed bus, depending on the demand. But the maximum speed that can be achieved through CAN bus, that is the 1 Mbps within a distance or within a length of 40 meter or 130 feet. So these are the things I have discussed in my very first class about this CAN. And the features or the characteristics of CAN includes that CAN is a broadcast type of bus. Broadcast type of bus means the common bus is shared by all of the functional components. Likewise, that the node A, we are treating node A as, for example, this is the automatic brake system, engine management system, node N, and if they want to interact with each other, so they will use the common bus. But if they exchange the data, if other nodes are there, other nodes are connected with the bus, they will have the same data or same signal. So in that sense, this is a broadcast type of bus. And as you can see that using a medium, some nodes are communicating with each other. So likewise, the data communication pattern, we have to follow some specific step-by-step rules. So whenever we are talking about step-by-step rules that are executed, or those rules are executed by mentioning some layers. Let's say that the directly access to the medium can be the signaling mechanism, the modulation mechanism, that can be handled by the physical layer, the modulation mechanism. Specifically, I will talk about that today. The modulation mechanism will be handled by modulation, or you can say encoding. Then the access mechanism, let's say the access mechanism to the bus are handled by the protocol layer. This is equivalent of data link layer in our data communication or TCP/IP protocol. And we have a message filtering layer, as CAN bus is a broadcast type of layer, a broadcast type of bus, as everyone is getting the signal, but everyone will not receive the signal. Based on some filtering mechanism, the nodes will filter out the unwanted signals. Only the node that is destined with the signal that will receive this data or signal from the bus by using the message filtering layer. So as we are dealing with the node ID, so you can treat this message filtering layer you can treat it as a network layer of TCP/IP protocol. So 3 layers, and we don't have any application layer because specifically this bus is designed uh, for the interaction between different types of embedded components. Okay, so I have covered these topics in my last class, and I have given you one basic configuration idea about that system, that we have a specific application, so we don't need any other application layer. Application layer is required whenever you have diversity of application software to run, but we have some specific application, that is the ABS, that is the EMS, and we have the host controller. This can be treated as the microcontroller, and we have a CAN controller area network controller, that is equipped with the physical layer activity, data link layer or protocol layer activity, and message filtering layer activity. And we have a transceiver that transmits and receives the signal to and from the bus. And you can see that we can achieve a maximum 1 Mbps of data rate within a length of 40 meter or 130 feet. And electromagnetic interference is also can hamper the signal or can hamper the data transmission. But if the CAN bus is shielded, in that case we can avoid the electromagnetic interference. So these are the things we have covered in my last class. So now today I am starting with this. So first of all, I'm talking about the CAN controller. You can see that this is the block diagram of CAN controller. So at the one end, CAN is connected with the bus. This CAN controller is connected with the bus. So this is bidirectional connectivity, because data can be traversed from to and from to the CAN bus or CAN controller. And in the right side, this is the host interface. This is the host interface. That means with the ABS, with the EMS, with the node, this host interface is connected. And this host has so many things to send. TX stands for transmit, RX stands for receive. So too many things it needs to send, and now it is receiving too many things. So this can be treated as the packet. And inside the block diagram, you can see that we have a CAN protocol controller. This is a microcontroller, and we have the acceptance filtering. That is the filtering layer works with this acceptance filtering based on the identity of the node. We have the status register. You know what is the status register. Likewise, the flag register, transmit buffer and receive buffer. So we have two separate storage. We have multiple of receive buffer, but we have single transmit buffer. So whenever the node wants to transmit anything, that will be stored into this transmit buffer, and whenever the CAN bus receives any signal or receives any data, that will be stored into this receive buffers. So multiple of registers or memories are used for the receive buffer. So the basic on CAN controller has a host processor. This is the host processor. You can say that we have the CAN controller that is responsible for receiving and sending, and it is a hardware with synchronous clock, of course. And we have the transceiver. Transceiver is responsible for it can be treated as the antenna, that it will transmit and receive the signal to and from the bus. Now, another vast feature that is, I will talk about the physical layer. Physical layer, I have already talked about that. In the physical layer, the purpose of using the physical layer is to make the encoding. And CAN uses the non-return to zero NRZ encoding method. You know that NRZ has some variations like NRZ-N and NRZ-L and NRZ-I. I guess you know that. non-return to NRZ L and NRZ I. So how it is defined? I guess you know that. Still, I'm just mentioning. Suppose one node likes to encode any data, that is the 0, 1, 1, 0, 0, 1, 1. Just NRZ will define it with a logical level. That is, let's say, if we say that the logical level with low means 0, 0, and logical level high means 1. So if we level out these things, the signal or data, the digital output, in this way we can draw a figure, or you can consider it in a vice versa way. Vice versa means you can consider high with 0, low with 1, no problem. But it's a logical thing. So as per this assumption, what we can do, so you see, this is the level. So this is another clock pulse. This is 1, this is another clock pulse, but this is 0. This is another clock pulse. 0, 1, and this is the level we have finished. So you see, these are the points of clock pulse. So these are not uniform due to my drawing, but you can just have an idea that these are the clock pulse, uniform clock pulse. So we have defined the NRZ L this way. Okay. Sometimes NRZ gives a more you can say that more robust encoding method. So that is the NRZ I. So either considering in 1 or either considering 0, whenever it will get the 1 or 0, the signal will be encoded into its opposite direction. So let's say that if we get any 1, the signal will shifted to its opposite direction. But if it gets 0, there will be no change. So let's see that how the NRZ I is designed. So let's say 0 is fine, no problem. But whenever at the very beginning of a clock cycle or clock pulse, if you get 1, so it will shift to an inverse position. Now again it is getting 1, so it will shift to an inverse position. And as we have considered that 0 means no change, so it is making no change. Now again it is getting 1, so it will make 1 bit change, or into this, whatever the condition, whatever the position is, just it will switch to the opposite state. So now it is 1, again it will. So this is the 0, 1, 0, 0, 0, 1, 0. So this is the encoding of NRZ I. This encoding technique is used in the physical layer. Either of these, as they have mentioned, that they have not mentioned that whether the NRZ I is used or NRZ A is used. But just I have explained both the NRZ L and NRZ I, and both can be used for CAN bus encoding. And sometimes NRZ L is also treated as NRZ M. M for mark, L for level, M for mark. Either NRZ. Yes.
Why did you write 0100 that one in NRZI? Because the thing which we got for NRZI was also for the upper bits mentioned above NRZL. We use that to get the NRZI thing.
Have you got the description of NRZ I? I stands for
Inverse.
inverse.
Sir,
Okay.
it inverted because there was 011 at first. So why did you again write 010 at first? Because
This one? Oh, this one?
Yes, sir. Yes, sir.
This one is the data, and this is the signal.
Yes, sir.
This is the signal, and this is the data. Okay.
Oh, sir, I got it. I got it. I got it.
This is the data. So let's say we with the CAN has a data, digital data of 0110011. Now, how this signal will be sent into the CAN bus? So this is our signal. This is using NRZ-L or NRZ-M, and this is if in case the NRZ-I is used, in that case the signal will looks like this.
Yes, sir, I got it.
Have you got it?
Yes.
Okay. So I think, and I guess that NRZ signaling encoding mechanism you have studied in your data communication course. Still, I have discussed using a simple example. But totally these things is logical. Sometimes in some cases, if any zero signal is received or zero signal is there, in that case we can make the inverse in one. In that case, for logical one, there will be no change. So it is totally logical thing. The NRZ for the implementation of NRZ-I, and also for the NRZ-L. So in that case, this can be opposite assumption can be made in that case. So this is one thing. Another thing is that the CAN has used with NRZ with bit stuffing. Bit stuffing. Bit stuffing means CAN starts with a start bit and CAN ends with an end bit. CAN starts with likewise the asynchronous communication. If you can recall that in our before midterm we have studied the asynchronous data transfer between the ICs or between the chips. So here as well they have the asynchronous communication, and they mark the data with a start bit, or you can say start byte, then the data or payload we say, and we have the end. Now, why do we need bit stuffing technique? Bit stuffing or byte stuffing technique. Suppose our start bit is with 1 and our start end bit is with 1. So in that case, we need start bit or bit stuffing. Or if we have the start byte end with a byte, so in that case we will have a byte stuffing technique. So both are both can be considered, but CAN bus has the option of bit stuffing. So let's say what is bit stuffing? I guess you know, but still I have given the example here. So this is based on the basic bit encoding. You see that with a flag, this is the frame start and this is the frame end. I have taken this from the data communication course, as because specifically for CAN I didn't find this sort of figure. So just to make you understand that this is our data, this is coming from upper layer. So let's say this data is coming from the access layer or data link layer towards the physical layer, and into the physical layer we have to add the start of the flag or start of the data, end of the data. So let's say the flag looks like 0, 1, 2, 3, 4, 5, 6, 0. So 8. So 0, 1, 2, 3, 4, 5, 6 and 0. So the flag looks like 1 byte. So I have considered 1 byte. So with this flag, in asynchronous communication, the receiver will understand, okay, that data has started from here and the data will end with here. But you can see that inside the payload or inside the data, if the data pattern looks like this flag, so in that case, there is a possibility for the receiver that the receiver will treat that, okay, the data has finished. So let's say 0, 1, 2, 3, 4, 5, 6. Okay, this is not the example. This is the example. Let's say 0, starting from this position. Starting from this position, 1, 2, 3, 4, 5. Okay. No, this is not that example. Okay, let's say 1, 2, 3, 4, 5, 6, 7, then 0. Oh, 1, 2, 3, 4, 5, 6, 7. I think the flag here it is considered is a bit, I've taken a wrong flag. Still, just the concept I am just giving you that if we have a data pattern inside the data, we have a data pattern similar to this flag or similar to this flag. In that case, in an intermediate time, so let's say the receiver started the reception of this flag. After this, it will receive everything. And if we have the flag type, flag pattern data, there is a possibility that the receiver will understand, okay, the data has finished in this position. Have you got this problem?
Yes, sir.
Okay.
Yes, sir.
Yes. So to avoid that, though my example might be not appropriate in this case, but just to make you understand about the problem, that there is a possibility of that for the receiver that the data is finished at this position. So it will be a misleading information to the receiver. So to avoid that, before sending the data, the sender stuffs some extra bit. So in that case, what it does, after 1, 2, 3, 4, 5, after 5 consecutive ones, it has inserted it has stuffed one extra bit, and you see 1, 2, 3, 4, 5. After 5 consecutive, if there is any 5 consecutive ones in your data, so just insert an extra bit. So after inserting these 2 extra bits, the data will be sent to the receiver, and this is at the receiver end. You can see the frame received. And after that, if the receiver receives with the data, it is the flag, fine. It is the flag, fine. But if in the interim time or interim bits, if there is 5 consecutive ones and we have an extra 0, the receiver will omit or unstuff the extra bits. So this is the concept of bit encoding. Why do we need bit encoding? Just to make some difference with the flag, with the start flag and with the end flag, so that the flag pattern data signal cannot be inserted into the payload, into this payload.
স্যার ঠিকই আছে স্যার, মানে 5টা 1 এর পরে যদি 0 দিয়ে
Example ঠিক আছে, right, example ঠিক আছে, though I cannot find the same pattern data here, but the logic is fine. The logic is fine from the flag point of view. It's okay. Yes. The flag pattern data I haven't found in these data, but if we apply this logic after 5 consecutive ones, if we insert or stuff 1 0, then even if the flag pattern data is available or present in the data, in that case it will work. I think you have got the problem, you have got the solution, right?
Yes.
So I have talked about the physical layer activity, that in the physical layer, the data encoded with the non-energetic signal with bit stuffing, and we have some other things for physical layer. The nodes are connected to the bus in a wired AND fashion. Wired AND fashion, that means some logical AND operation need to be made there. So what is wired AND fashion? If just one node is driving the bus to a logical 0, then the whole bus is in the state of logical 0. You know, in an AND operation, if we have a false condition or we have a 0 value, for bitwise operation, if we have a 0 value, the whole result will be 0. So in just taking that advantage, the wired AND fashion has been implemented. I will discuss about wired AND fashion in coming slide. And the maximum transfer rate is 1 Mbps or 1000 kilobit per second in a maximum length of 40 meters. But if you increase the size, the rate will be decreased. And the maximum data length, the length of is short with a maximum 8 data bytes per message. 8 data bytes means 64 bits. Okay, 8 data bytes means 64 bits can be sent in a single data packet from one node to another node, and it is based on the design consideration of low latency. And also for checking the error, you have seen that in our asynchronous communication in pattern, I have shown you the parity checking, parity for checking the error, whether any error has occurred in when the data transfer has needs to be taken place between the components. So in that case, also they check the error using the CRC, but not CRC32, rather a lower version of CRC, cyclic redundancy check. So I've talked about bit encoding. Let's talk about the, I have completed the physical layer activity. So you see that we have the physical layer. In physical layer, the encoding is with NRZ, with bit stuffing, and we have the maximum speed, and it is operated in wired and fashion. Now I'll talk about the protocol layer. Protocol layer is the equivalent of data link layer, where the medium access control operation needs to be explained. First of all, the bus is accessed, the bus access is handled via the advanced serial communication protocol, that is the CSMA-CD. And you know that for Ethernet we use for Ethernet data communication, we use the CSMA-CD. Carrier says multiple access with collision detection. That means multiple node will access the medium. If anyone detects the collision, it will send a jam signal, or it will send a notify signal to other nodes that one collision has been detected. But they have added with a non-destructive arbitration. Non-destructive arbitration means no collision or no interference will made by the nodes with each other, so that they make some arbitration technique using non-destructive approach. I'll discuss. And this means the collision of the message is avoided by bitwise arbitration without loss of time. So they will make some bitwise arbitration. I will show you that. There is no explicit address in the message. Instead, each message carries a numeric value which controls its priority on the bus. So in the message, there will be no explicit address, rather some identifier value will be used, and the lower identity value will have the higher priority. That's the thing. The numeric, considering the numeric value, the lower identity value will have the higher priority into the bus. Let's say these are the things I will discuss about while I will talk about the frame. So here is the CAN bus characteristics based on the wired and fashion. You see that one is a state by any node. If any node sends any signal of 1, that is the recessive state. And if any node sends a 0 signal, that is the dominant state. And you see that 3 nodes, A, B, and C, if you consider these 3 nodes are connected into the bus, let's say A, B, and C. If any one of them, or if every one of them is sending 0, 0 means dominant, then the bus status will be dominant. Fine. If any 2 of them is sending dominant and one is sending 1, or C is sending the logical 1, still it is in the dominant state. And you see, if only one dominant state is there, likewise here, only A is sending a 0 signal and other 2 is sending 1 signal, still the bus status is dominant. And you see, only when the bus status will be recessive, that is the everyone is sending 1. So this is the wired and logic, that using these 2 logic states, that is the recessive and dominant, the CAN bus works. How? Let's see. So recessive RRR, and node A is sending the dominant signal. The whole bus state is dominant. And this is the CAN transceiver. You can say the transceiver, we have seen the logical diagram of the transceiver, and this is the bus. And the voltage level always maintained with the 5 volt. So let's see that CSMACD with non-destructive arbitration. And you see that we have node A, B, C with node X, another node. So let's say that A, B, C has data to send, but X has taken the control of the medium. But in this position, the medium or the bus become idle, because X has completed the transmission here, and just after that, everyone senses the medium is what? The medium is idle. And in that case, what happened? If everyone sent, if we don't have any arbitration, so in that case, what will happen if we don't have the arbitration, or if we don't have this purple color? So in that case, what will happen? A will immediately send the data. B will send the data immediately, and C will send the data. So in that case, there is a possibility of collision. Have you got the problem? We should have some arbitration to avoid the potential collision, so that multiple nodes cannot send the data at the same time. Have you got it?
Yes, sir.
Okay. So to avoid that, the nodes will send the data, fine, but they will send their identity. They will send their identity. The node that has lower identity, so let's say one node has, if I consider 4-bit, one node has, that's 8, 1 0 0 0. This is 8. Another node has 1 0 1 12. Another node has 1 0 1 1. That is 13. So this is the identity of A. This is the identity of B. And this is the identity. For this example, I will consider this is C. This is the identity of C, and this is the identity of B. Now, in the medium, let's say this is the medium. Everyone is sending the signal. Just this is the position that the medium is idle. A will send 1, 1 1 1. So the medium will be what? Recessive. So no one will have the control. Then 0 0 0. This is the dominant. So everyone has the control. So everyone knows that, okay, the status becomes 0. Okay, I have sent 0. So that is why I have sent 0. That is why the medium is dominant. So everyone will think that I'm the dominating node. But they have not finished to send their identity yet. In the next case, A is sending 0. And other two is sending 1. So now the status of the bus will be dominant, and C will understand, okay, I have sent 1, but still the status is dominant. B will sense that, okay, I have sent 1, still the medium is dominant. And A will understand, okay, I have sent 0, and the medium just becomes 0. So I have the control here. I have the control here because he did it first. So this is how C and B will identify themselves as a less prioritized node, and A will complete sending its whole identity. Have you got this logic?
Yes.
This is the logic of non-destructive arbitration, and you see that is why here A has started sending the data, and as per my example, in this case, C has started sending the C first in the third cycle, and in the fourth cycle, the rest B will send the data. So this is how we are actually using the carrier sense multiple access with collision detection with some non-destructive arbitration, and this non-destructive arbitration is based on the identity of the nodes and using the word and policy as well.
বাট স্যার এখানে স্যার একটা স্টারভেশনের সমস্যা হতে পারে না স্যার?
স্টারভেশনের সমস্যা হতে পারে, ইয়েস, হতে পারে যদি কোনো নোডের মানে সবগুলোই ওয়ান থাকে, there is a possibility of starvation, of course, but for your information আমি বলতে পারি যে this is a lightweight protocol and very low load, low speed and low data rate protocol. So in that sense, everyone will have the access schedule.
ওকে স্যার, থ্যাংক ইউ।
মানে lightweight means traffic load is less. If you consider with the Ethernet has huge data volume or data rate we need, but in this case it's a very lightweight এবং low load অ্যাপ্লিকেশনের জন্য এটা প্রপোজ করা হয়েছে।
জি স্যার, বুঝতে পেরেছি।
So very good observation. My field is wireless communication, so there as well starvation is a problem, and still the standard of 802.11, this is a very unfair protocol. I say that is the wireless LAN Wi-Fi standard, the wireless LAN standard as well as the later versions A, B, G, N, AC. Now we are working with AH and AX. So specifically for Wi-Fi standard, we have found that this is a very unfair protocol because starvation option is there. So in that sense, we say that CSMA-CA is a CSMA-CA with the standard 802.11. We say that's an unfair protocol due to the starvation. Okay, so the bus transmission speed. What is the time? Okay, still we have 8 minutes. Hopefully I can finish it, inshallah. And the bus transmission speed, you can say that the maximum speed they have considered with the propagation delay. That is, the data will go and data will send from sender to receiver and receiver to sender. There is another time. Considering that time, that means the twice of the propagation time is considered as the maximum speed. Considering that the maximum speed is treated, and you can see that within the 40 meter length we can achieve that maximum speed. Beyond less than 40 meter, we have higher speed, but it's a trade-off. You can consider that less than, if we need less length, if we use less length bus, then we may adopt less number of components. So 40 meter is a standard size they have made, and using the twisted pair, of course. Okay, so the CAN protocol. Now I'll talk about the data frame. In case of CAN protocol, the 8-byte message, 8-byte means 64-bit message. 64-bit message can be transferred from node A to node B using a shared communication medium. And we have the node address, we have the flow control and establishment of communication. How? Let's see. The CAN standard has 4 types of data frame, or 4 types of frame. One is data frame. Of course, the data size is 64-bit or 8 bytes. We have a remote frame, we have an error frame in any case of error. If is detected, in that case only error frame will be sent. In case of overload situation, the overload frame will be sent, and in case of some polling, the remote frame will be sent. So first I will start with data frame. So CAN has two versions actually. One is CAN 2.0a, where the identity of the nodes is explained with or derived with 11-bit, and CAN 2.0b, that is an extended CAN. We say this is the standard CAN 2.0a, and extended CAN is 2.0b with the identity value of 29-bit. And you see that the arbitration field, arbitration means this is the start of frame. You already have that idea that this is the start of frame and this is the end of frame. So let's identify this first. This is the start of frame. So whenever one node is sending the data, this is the start of frame. The one is start frame delimiter it needs to send, and this is the end of frame. And at the very beginning, the node will, before sending the data, the node or control field, it will send the identity, and this identity will work for the arbitration, whether that node is has the priority to access the medium or not. So that is identified, this identifier, and how that is already I have discussed in my last slide. And here as well we have the arbitration, but the extended is used only when the number of nodes, higher identity means higher number of components. Lower identity means lower number of components. 2 to the 11, it's a huge number. So this is standard, it's a standard. This is the optional, but you see that 2 to the 29, so many CAN components or embedded components can be applied in a single embedded system. So this is just an optional thing, but it also works with the 11-bit first for the arbitration. If this is within this, the arbitration is not done, only then the extended version will work. Okay, after that we have the data field, and you know that already the data field has 64-bit with a control with some control information. We have the cyclic redundancy check, and it is the trailer. Why we need the trailer? Why we have to check the data? For error checking is done after receiving the data, because until and unless the node or receiver receives the data, it cannot identify whether any error has occurred or not. So based on the CRC field and based on the data field, the node will identify the error. If any error occurs, only then in the remote frame will be used. And after getting the data successfully without any error, one acknowledgement slot is there. One acknowledgement slot is there that the receiver will send the acknowledgement. And after that, the data frame will be finished. So this is the way that the node will exchange the data frame. Now about the remote frame, this is for the standard type of remote frame. We have the arbitration field, we have the control field, we have the CRC field, and we have the acknowledgement field. And generally the data transmission is performed on the autonomous basis with the data source, that means a sensor of a component sending out a data frame. But it is also possible for a destination node to request the data from the source by sending a remote frame. That means it's a request that say you are a receiver, but you are requesting me, sir, send me, I am now free, send me your data. So that request will be sent into this control field, and there will be no data. You can see there is no data. So the remote frame is used for requesting some data from a particular node, and the other things are similar. Likewise, the arbitration field, CRC field, acknowledgement, and end of the frame. Error frame, already I have talked about that. Why do we need error frame? If any error is detected by after getting the CRC, after receiving the CRC, cyclic redundancy check field. If any error is detected, only then the error frame will be sent. And there are two types of error flags into this error frame. One is active error flag. These are six dominant bits they sent. Or passive error flags or 6 recessive bits is sent after receiving the data. That means 6 dominant bits. This is the error notification by active error flag. So this is a flag with 6 bit, or a passive error flag with the 6 bit, but 6 recessive bits will be sent towards the sender. And finally, the overload frame. I think it's the finish. Okay, and already it's 9:50. Overload frame. Overload frame means if any node is overloaded with the data, that means the buffer. You already have that idea that if the receive buffer is full of data, if the received buffer is full of data, that means no further data it can be received. So in that case, this node will send the overload frame. So how? It will just send, I'm very busy with another, with busy little with this is the device ID. Could you please wait for a moment? So the error frame structure is not given here. The overload frame and error frame structure, they have not given here, but still it's a frame to notify the other nodes that I'm overloaded, but my buffer is almost full. So this is another option. So that's it for the CAN bus. Okay, total 21 students have attended this class. So this is an interesting protocol considering the embedded protocol, and I have finished it today. Hopefully in the next class, I will start with another embedded protocol or embedded bus system, that is the interconnection IC bus. Do you have any question regarding control area network?
Sir, what is the role of RTR in the diagram?
Request to receive. Request to receive can be considered about RTR. This is the request to receive. I forgot to mention the request to receive. Okay, though this is a position. This is a position from where any frame can be sent. This is the identifier. This is the common thing, and request to receive to start the data frame, to start the remote frame, or to start the error frame or overload frame. So this is the position from where the actual data is started, but no signal is there. Everyone is initiated the communication by their self. After sending the identifier, they will start sending the data. And this position you can treat with this with this position. You can see this is the position that at that time the node is founding the medium is idle. But this is not a signal anyone is sending. Any other question? Okay, so what I will do that I have another reading article. Okay, I'll take 1 minute more. I'll take 1 minute more. So this is a reading article. I think you can see that this is a reading article. I'll give it to your Google Classroom, and everything is more clearly mentioned in this reading article. So you can see that the ID allocation, bit timing, though everything is covered in the lecture slide, but still for your reference, this reading article I will provide to you. Okay. So thank you, and hopefully today we have